All right, guys. There's a note up here. Not sure that everybody knows there is free counseling services. Need to put the word free in there. Really big letters. So, if you need counseling, it's available. There's a phone number and an email to contact. And I strongly encourage it. They're a good service. I had one student who was having problems actually with a professor at another school. She was going to both schools. And they helped her out. They helped her out, and actually it worked out. You know, contact was made with the other school and everything, you know, with her permission, and everything was handled. These are good people. I strongly recommend them. So what we're going to do today is go through how to think like a computer scientist. We haven't been using this so far, but we are going to do so now. We are ahead of it actually, because we've already been using the concepts. So this is not going to take us long to plow through chapters 1 and 2. So chapter 1, you remember how to get here. You just go to the content section and hit textbook. This is a really important line. The single most important skill for a computer scientist is problem solving. Really, that's what you're doing. You have a little puzzle that you need to solve. Or it could be a big puzzle, and you work your way through it. You work your way through it first by determining the logic, and then by determining the lines of code that will implement that logic, and then by fixing whatever's wrong with that logic. So there's several steps. So Python is a high-level language. There are other ones. You know, at school here we teach C++, C#, Java. Those are all good languages. They all have somewhat similar syntaxes. So once you learn this one, you have a leg up on learning the others. And additionally, even more importantly, once you have the concepts, you can apply the concepts. The ideas like variables and setting, you know, values and doing loops and logic statements, you know, if then and or, all that stuff applies to every programming language. So when we launch idle, it actually goes into the Python interpreter. We've seen this before. We get that Python prompt with the arrows there. We can see that all by itself without going into idle. If we launch the command shell first, I may have had you do this on the first day. You click on the start, you type CMD for command shell. Or if that's not doing it for you, you can hit the Windows key and R for run and type CMD. Then we get that. And then if you type Python, it dumps directly into the command shell. Now what do you do in the command shell? We're not going to do a whole lot in it, because we like writing scripts. We like writing programs. But what we can do is we can test out little concepts. We can, you know, just a second, let me make the font larger. Like the idea of variables. A is equal to 3. Print A. What is the type of A? A is an int. That kind of stuff. You can even write multi-line commands if you want. You could actually enter an entire program. You know, if you had a 200-line program, you could just enter it directly into the shell, but it's going to try to execute the lines as you enter them. So, and if you make a single syntax error, a single typo, it's a real drag to try to correct. So we're not going to do that, but we could. For example, here's an if statement. If A is equal to 3, colon, print hello. And I did a syntax error. Expecting an indented block. All right, we're going to try it again. If A is equal to 3, colon, hit the tab key, print hello. Now it wants me to stop tabbing. It's not going to execute this if statement until I stop tabbing. And it actually executes it. So you could test logic out and stuff like that, but just about every time we do anything, we're not going to go straight into the command shell, into the Python prompt. Sometimes I call it the shell, sometimes I call it the prompt. I usually call it the shell actually, but this text here is calling it the prompt. So anyways, instead we're going to launch idle, and when we launch idle, it pops open to the same thing. But notice that when we ran it that way, there's no file new command, there's no run command. You're just, you're in raw Python mode there, and if you wanted to write a script, you'd have to go to a text editor like Notepad or something and write it. We're not going to do that. We already have a text editor. It's idle. So when I launch idle, we see our Python prompt again. We see our Python shell. We can do the same kind of things we were doing, and it's easier to read. A slightly larger font. Now we never do a save as on this because this is just a recording of what is going on. It's not a program. If I try to do a save as and then I try to run it, it's totally not going to work. Instead I have to do file new, save the program, write it, save it again, and run it, This text shows something called PyScripter. If you feel like installing PyScripter on your machine at home, you can. There are a lot of other Python tools as well. There's one called PyCharm. We're using idle because it comes with Python. You don't have to download an extra editor. Maybe these do some cool things that ours doesn't, but eh. So what is a program? It's a sequence of instructions. I gave the recipe comparison. A recipe is a program. It programs a human to bake a cake. Or you have a series of instructions for building, your IKEA shelves. Whatever. That series of instructions is a program. Now it's got lots of diagrams and stuff, but if it was purely text, that would be a far closer example of a program. So the program, it's a series of instructions. And since it's a computer, we're specifying not how to bake a cake, but how to perform a computation. The computation could be something mathematical. Calculate the volume of pi. Calculate how much interest you've earned over 10 years. Calculate your body mass index based on your height and weight. Calculate the roots of a polynomial. Whatever. But it can also be symbolic computation. If you type in words, those are really symbols as far as the computer is concerned because they're numbers. Everything is a number underneath. All the words that you type into a word processing program, all the sounds that you hear, all the pictures that load up, they're all numbers underneath. But if you go into a program and you start editing text, you put in a name or whatever, you write a document. Those are symbols, and you can manipulate them with a program. Like if you want to search your document for every occurrence of the word Obama and replace it with Trump, you could do that. Search and replace. That's a symbolic computation. Completely different than doing math. That's not math at all, but it's still a computation. Our basic computational building blocks are pretty much the same throughout every language. You have input. Input's typing into the computer, or it's reading from the internet, or it's reading from a file. It's reading from a sensor, a light sensor or a pressure sensor or something if you're doing robots. Output, displaying data on a screen, sending data to a device like a speaker, or sending data to a file or posting something on the internet. Math, we know what math is. Conditional execution, if something matches a certain condition, do something. If it doesn't match that condition, either do nothing or do something else, like an if or an if else. And a repetition, when you repeat something over and over. Believe it or not, that's pretty much all there is to it. Every program you've ever used is made up of instructions that do these kind of things, no matter how complex the program is. So what is debugging? Debugging is when you write a program but it doesn't behave the way you want it to. Very common. Everybody debugs. It's not something that you get over, once you're a beginning student. It's not like you start writing code that's perfect. That's pretty much just flat out impossible. If you were a professional ice skater and then your coach showed you a new routine to do, there's no way you could go out there and do that new routine perfectly. Same thing with writing a program. Even though you have all the concepts in your mind, when you write it, it's not going to be perfect unless it's an incredibly short program. So you have to fix it. There are 3 categories of problems. I've already mentioned 2 of them, syntax errors and what I called logic errors, which this text calls semantic errors. Syntax error is a typo, or you garble a syntax. So if you say, go 5 miles, then 7 glorps. Obviously, that's incredibly bad syntax. We have no idea what any of that means. We could correct it. Go north miles 5, 7 miles west. Something like that. As humans, we can work around, slight mistakes in syntax, which is why we can understand, if people, who weren't trained as native English speakers, they're talking to you and you can understand them even though, they may be, mixing up words or putting them in the wrong order or whatever. Humans can interpret stuff like that, but machines can't. Machines need them to be pretty dang specific, and so it's actually, a lot of effort goes into making things like Hey Google or Siri or Cortana able to respond to natural language requests and figure out what the heck you mean. So this is bad syntax as far as we are concerned. We could figure it out. It means go north 5 miles and then go 7 miles west. But if it's pretty bad syntax, and what if things were even worse? What if things were out of order like that? We don't even know what that means. All the words are spelled right, but it's still bad syntax. Then you can have a logic error. That's when you say go north 5 miles, west 7 miles, and you want it vice versa. I'm going to change these, yeah. Okay. So, syntax, logic. Textbook calls it a semantic error. The syntax is perfect, but we really wanted to go 7 miles north, 5 miles west. So we wind up in the wrong place. We get the wrong answer. Then there's a third kind of error, runtime errors. Runtime errors are unexpected cases. You have perfect instructions. Go north 7 miles, west 5 miles, but oops, you hit a tree. That's a runtime error. You run out of gas, you have a wreck. Your friend calls you and says to come over instead. There's anything that could interrupt the successful completion of this task. Tire blows, whatever. Those are all examples of runtime errors. A runtime error is a state that the program gets into when it doesn't know what to do next. And an example of that would be something like this. Say we write a little program that asks the user for information and then tries to convert it to an int. It's going to be real easy. I'm going to make it as simple as possible.
So I'm going to just call it save as, call it RTE for runtime error. I'm not really fixated on the idea of you entering this, but you could. Here we go. So x is equal to input, give me an integer. And then x is equal to intx. Perfect syntax. It'll work beautifully. Until your testing department decides to give it some bad data. Because programmers, they write code and then they test it to make sure it works. It's a bit of a different paradigm shift to test a program to make sure it fails. You don't want it to fail as a programmer, so you don't test the failure conditions. But the users of your program sure are going to find a lot of failure conditions. And to prevent that from happening, then larger places, programming teams will have somebody devoted towards testing. Same idea as beta testing. You ship out the code and you find out that the computer crashes when you click the close box or something like that. Or you're doing game development and you have gamers who find out that the music becomes silent at a certain point or whatever. So anyways, this works great. You run it again, you are now trying to make it fail. Well, what if I don't even type a word? I mean, type a number. It blows up. The program stops running. It doesn't know how to handle that. It doesn't know what to do next. I run it again, and I type in a number, but maybe as a user I didn't know what an int was. So I typed 10.1. Again, it blows up. So that's a runtime error. There's all sorts of runtime errors you can run into. What if you try to open a file to read from, but the file doesn't exist? Somebody went in and deleted it. What if you try to open a file, but you reference a drive letter that doesn't exist? Your machine doesn't have a D drive, but you tried to get to it. What if you're opening the internet, but the internet is down? Or the server that you're trying to access, or you mistype the URL. There's any sort of problems. It would be really annoying if I was using an internet browser and I typed in the name, the path to a server, but I got something wrong, like that. Well, thanks, Google. http://google.com. I'm mistyping it. Google is correcting it for me. Thanks, Google. It would be really annoying if when you typed in something wrong up here, instead of getting an error message or Google trying to fix it, which it is, it just shut the program down. Displayed a red error message and it couldn't do anything else. So your goal as a programmer is to write bulletproof code that can handle that kind of error. If you try to open a Word document and that document didn't exist and then Word quit, that'd be annoying. But what if you had written a document and you tried to do a save as and you saved it to a bad file name or a drive and that drive wasn't there and so it quit? Well, great, I just lost my term paper. You're trying to write programs that handle that kind of condition. Now, we don't know how to do that at first. We don't even know how to stop that int function from crashing. But we'll learn. Syntax errors we've covered. Runtime errors we have covered now. These are also known as exceptions. You'll hear the word exceptions. Something exceptional and bad has happened. What does exception mean? It's not normal. It's not expected. It's unexpected. So whenever you hear the term exception, it means a runtime error. And you use that term a lot in Java programming and other languages that have a lot of support for exception handling. Python does too. Semantic errors are logical errors. So what happens is when you're trying to fix your program, you do experimental debugging. Experimental debugging, you make a change, see if it fixes it. You make another change, you see if it fixes it. Maybe your code only blows up when you type in 0, and then eventually, working through it, you figure out that there was some equation where you divide it by 0. And so as one of your experimental changes, you put an if statement there so that if equals 0, then you handle it gracefully rather than generating a runtime error. So experimental debugging, it's a skill that you grow into. And in class, whenever you're running something and you get an error, I'm probably going to run over there and fix it for you. That doesn't really teach you a lot, but I can't let you bang on something for 30 minutes trying to figure out what's wrong, because otherwise you'll wind up with key marks on your forehead. You won't like it. Well, realistically speaking, we just need to keep the class going. Hopefully, when I correct something, you watch it and see what I did. If it's a syntax error, it ought to be really clear. I'll just say semicolon there, colon there. You forgot the parentheses, that kind of thing, and you'll be fixing it yourself. But logic errors, I may type something in for you if I can't communicate well enough what you need to type. And I still want you to learn from it. That's why we have homework as well as classwork, so that you get a chance to write your programs and debug it yourself. If you get totally stuck, take a picture of it, send it to me. I'll work on it with you. Some of y'all have already taken advantage of that. And if I don't answer your text, send another one. I apologize if I've slipped up on anybody. All right, we're going to scroll down here. Scroll down here. You can read this all. Wouldn't be a bad idea. But if I don't talk about it in class, and if I don't type an example of it, then it's not going to be on an exam. That doesn't mean it's not worth reading. The first program, print hello. We've already done that. That means that print is a function. And since it's a function, it has a parentheses after it. It has a pair of parentheses. All function calls have parentheses, whether you're passing data to that function or not. If you just put the word print without any parentheses, it's not going to print. Now, in earlier versions of Python, they made print something else, and you actually could use it without the parentheses, but that's been changed to make it consistent with every other function. So if you ever take a Python 2 program and it doesn't run in Python 3, you run through and you fix all the new syntax errors. Comments. We know what comments are. Every program you write, I want you to put a comment block up at the top. Even if it's just an in-class assignment, put your name and date on it. It doesn't take that long. I also want you to say what the program does. Now in class, you don't really know what the program does until we're done with it, because I'm typing examples up here. And so if I don't give you an explanation right off the bat, I'm not expecting you to tell what the program does. But for homework, you can. This program converts Celsius to Fahrenheit, or C to F, that kind of thing. This program calculates, body mass index, or this program calculates interest, or this program simulates a dice game, whatever. You can explain it in just one sentence. You don't have to write an essay. But I really do want your name and your date in it. You just need to get in the habit of documenting all your code. John Carmack, the author of the Doom, video game, went on to do Quake, and then he took that graphics engine and licensed it to other companies to make three-dimensional games, and he made a huge amount of money doing that. And then he had to keep improving it, because competitors were coming out with games that would look better. Obviously something would look, better 5 years after Quake. So he had to keep improving his code. And if he didn't document his code, if he didn't add comments in it, there's no way that he could come back and understand what he had written well enough to maintain it well. Especially when you have teams of people. Say you hire somebody. If you have a code base of 5 million lines of code and it's complex code, and then you hire Joe and you tell Joe to fix something. If there are no comments in the code, it's going to take them a long time to figure out how to fix it, if they can. They may put in more mistakes than there were to begin with. So you need to comment. All right, here's a glossary. If I run through this, people are going to get sleepy. Algorithm. An algorithm is a series of steps for solving a problem. It's not a program. A bug, an error. We talked about 3 kinds of bugs. A comment. We know what a comment is. The computer ignores that it's meant for the other programmers or anybody reading the source code. Debugging, the process of finding and removing bugs. So did I show you all the first computer bug? First computer bug. There it is. Okay, now that's back when computers actually had mechanical components as well as electronic ones. had relays. You know, relays are things that close and open mechanically to determine where the electricity is going to flow. So Grace Hopper, very, very early computer scientist, but she was active for an incredibly long time, incredibly influential. Anyways, the computer stopped working. She opened it up and found that there was a moth stuck in the gears, you know, in the relay. And so she put first actual case of bug in her notes. That was kind of a joke because the term was already in use. It dated back to electrical engineering. Some say that it dated back to, you know, Thomas Edison. So, you know, a bug is just a mistake. You could have bugs in the machine that stopped it from working, but nowadays they're not insects. I hope not. I don't want bugs in my phone. Alrighty. Whenever I go through a PowerPoint, I strongly recommend you, kind of expect you to go back and read it on your own time to hit the parts that I missed. And the glossary is like that. A script, that's a program stored in a file. You know, a text file, really. As opposed to when you write a C++ program and then you distribute that as an executable, as an app. You distribute your Python program as a .py file, which just is text. Source code is the program that you write. It's different than pseudocode. I had somebody ask for help on the pseudocode assignment, and they were throwing in things like print, you know, an input, x is equal to input. They were trying to write the program, and it took them a while to figure out that pseudocode is something different than the program. So I had to go back to the assignment and show them, no, the pseudocode is this part. The programming language is written like this. The pseudocode is like the outline of an essay, and then the programming is the essay itself. Okay, we're not going to do these exercises. Alrighty, chapter 1. See how fast it was? We're going to be done with this class in a week. Okay, I'm kidding. But variables, expressions, and statements. We already know what a variable is. Value. Values are fundamental units of information, like letters or numbers, that the program manipulates. You know, I need to download the extension that just increases the size of the font without zooming in, because when I zoom in, we have to scroll around to see it all. But I'm not going to take the time to do that this time. We've seen 3 different kinds of data. We've seen numeric data, we've seen integer data, and we've seen string data. String data is what you get when you let the user type something in, and you have to convert it to numbers if you want to do some math. If you want to indicate a string, you have to put quotes around it. A lot of people do things like this as an introduction. Print. Hello. There. Ought to work. Doesn't work. Got to put the quotes. This language doesn't care if you use single or double quotes. A lot of other languages are picky. Double quotes indicate a string, and single quotes indicate a single character, like that. This language doesn't care. Alright, it's not legal to put in commas, so if you're trying to type in 1 million, you can't do x is equal to 1 comma 0 0 0 comma 0 0 0. Even if that doesn't give you a syntax error, which I played with yesterday and I don't think it does. It doesn't do at all what you think it does. Let's play with that. Let's go back to idle, to Python. X is equal to 1 million. Yeah, cool, it's not an error. It's going to work, right? Well, I'm going to print it out. That doesn't look the same at all. That's using concepts that we haven't seen. So, don't put commas in. Not that you were tempted to. If you want to allow the user to type commas in their input, then you have to go through and remove them before you try to convert it. Or you just tell them they can't. So variable, you've got a string variable here. You've got a numeric variable here, an int. You've got a float variable there. A variable has a name, it has a type, and it has a value. I've said that a couple times. I swear that's going to be a test question. The assignment token. What is a token? A token is just a piece of something. If you type in Jeff Johnson as your name, and the computer's trying to figure out what your first name is and your last name is, this is actually considered two tokens. Everything separated by a space in your input is considered a token. Or if you're writing a compiler that figures out what a language is, like that. The word if is a token. The variable x, the literal, because you literally typed a 1 into it, is another token, and the equal signs are a token. So there's two different tokens here. You'll hear the word operators. I'm not going to use the word tokens hardly ever. But these are two different operators. This one is for putting values copying a value into a variable, and this one is for comparing them. X equals 3. If x is equal to 1, do something. If I type this, x is equal to 3. If x is equal to 1, and I'm putting parentheses where they're not necessary, because I teach 3 other languages where the parentheses are necessary. That would make a Python programmer look askance at me, but it works perfectly well. So anyways, this code flat out would not work because we use 2 equal signs and we use 1 equal sign. And did I already give the little lecture about when I'm saying code, I may not say equal equal. I may say something like this. X equals 3. If x equals 1, colon. What I'm going to type, because I know this, is that the first use of the word equals is a single equal, because there's no comparison going on, and that the second one is a double equal. I will try to say equal equal, but I may forget. So you just need to remember that. Plus you get the visual clue. You can look up here and see what I did. Variable names versus keywords. The language has keywords. When you're writing a program in Python, some of the words are highlighted in orange. If x equals 1, colon, print hello. The word if is a special word. It's not a variable name. You can't use it as a variable name. If I do if is equal to 3, that's going to be a syntax error. It's not going to even run. There are others, so you cannot name just put know the difference. So, variable names have to follow a few rules. 1, they can't be keywords. Do you have to worry about that? Not very often, because very rarely are you going to say while is equal to 10, or if is equal to 3, or, def is equal to 10, If you type something like that and it gives you an error and then you see that the word is orange, you just go, oh, that's one of the language's keywords. I can't use those. Keywords are the things that make up the language. They define the language. So if it shows up in orange, don't use it as a variable name. Also, if it shows up in purple, they should not be function names. Now when I say should, they can be, but they will break the code. What if I do this? Print is equal to 10, and then I do print x down here. This is legal syntax. That's not going to give an error. That's not going to stop it from compiling. However, this is going to be a runtime error. We're going to run it and it's going to blow up. Boom. The reason why is we have redefined what print is. Print is no longer a function anymore. It's a number. So throughout the rest of the program, we can no longer use the print function. So you don't want to use variable names, function names as your variable names. And there are times when I make a mistake and I have to fix it. I love the word sum. I'll use sum is equal to 0, sum is equal to x plus y plus z. Then I'll notice, oh, it's purple. I need to choose something else. Capital S for sum, that'd be great. Or I just come up with a different term that means the same thing. They should not be function names, or else they destroy the meaning of the function for the rest of the program. Here's a set of the keywords. By the time the class is done, we're going to know what a lot of these are. Not all of them. You can certainly find out what the rest of them do. The documentation is all available out there. Statements. A statement is a command to the computer. These are all statements. That's a statement. First one. That's another 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 one. One thing you cannot do in this language that you can in others is to chain multiple statements on the same line. X is equal to 1, semicolon, y is equal to 2, colon, z is equal to 3. I'm going to move this so that it actually would have a chance of compiling. When I run that, what do you know? I said it wasn't going to work, and then maybe it did. One plus 2 plus 3 is 6. That works totally fine. Let's play with that a little bit. Print I print love print programming. There we go. Well, what do you know? Okay, you can. It's considered bad form even in the languages where it's explicitly called out that you can do that, like C++. Usually the only time you want to do that is if the actions are very similar. Here we're creating 3 variables and we're assigning 3 values. That's real clear. Doing stuff like this, I'm going to add those 2 together and then print the total. Don't do that. So pretty much in our class, just assume that you should only put 1 statement per line. However, you can combine function calls. I could do this. X is equal to print, well, I could do this. X is equal to input, hello, or number, please. And then X is equal to int X, and then print the number was, comma, X. I could do all that in a single line if I wanted to, and it's not really combining statements, it's building a very large sequence of function calls. It would look like this. I don't want you to do this. The number was, comma, int, input, number please. That'll work. Is that easy to understand? Well, maybe after you get a little bit more skilled. But you can embed a whole bunch of function calls like that and make code very difficult to understand. Don't recommend doing it. One exception is just the input statement. If you feel like doing this, X is equal to float, input, what is the temp in Fahrenheit? Knock yourself out. You'll see a lot of code out on the example if you Google up code written like that. Why? Because if you just have a single line of pseudocode that says input temp or input X, this lets you do it in 1 line of code in Python. Why not? I'm not expecting you to, but you can. you'll see that, and I do want you to understand what's going on. It gets solved from the inside out. It keeps looking for parentheses, it finds the innermost thing. Oh, this input call is the innermost thing. So it does that first. It calls the input function, which displays number please and accepts input from the keyboard. Once they type something in, that's like the innermost shell of one of those dolls, you know, the nesting dolls or whatever, then, or the innermost thing of an onion, it goes out to the next level, which is taking what was returned by this and passing it into the int function. That gets converted to an int. That comes back out and it's passed to the next shell, the outermost shell, which is part of the print statement. Alrighty, just like the last class I did, we're probably not going to actually have a legit in-class assignment for this one. Doesn't mean I don't want you to type along and play with these ideas. It's just we're not coming up with an overreaching concept. Evaluating expressions. An expression is a combination of values, which can be called literals, variables, operators, and calls to functions. So what's a literal? It's either a number or a string in the source code. And what do I mean by that? One is a literal. It's literally typed into the code. Joe is a literal. That kind of thing. Then there are other things. There are variables. We know what variables are. You know, A, X, temperature, things like that. Then there are functions. Int, input, float, and plenty of others. And we will write our own functions real soon. Then there are operators. Operators are the symbols. We usually talk about mathematical operators, but there are others. Addition, subtraction, multiplication, division, floor division, modulus. So an expression is a sequence combining variables, literals, function calls, and operators. It can just be one of those things. X is equal to 3. That's an expression. X is equal to 3 times y. That's an expression. X is equal to 3 times y times integer of the value 10. That's an expression. X is equal to 3 times y times the integer value of the input. Please enter your age. Something like that. Those are all examples of expressions. Typically, when you hear the word expression, you think of something that has an operator involved. There are other kinds of expressions too. Logical expressions. Those are all math expressions. Those are arithmetic. Others, logical. X less than 3. Y equals 2. B is not equal to 10. B is not equal to 10. And X is less than 3. Those are all logical expressions. An arithmetic expression evaluates to produce a numeric value, whether it's an int or a float, whatever. Then there are the logical expressions, which all evaluate to either true or false. Operators. Operators are the symbols. Operands are the things that are on the sides of the symbols. In this code, less than is the operator. X and 3 are the operands. Those are the things that feed the X. They feed the less than sign to get it to work. Equal equal is actually an operator. It's a comparison operator. And what are its operands? How many operands does it have? It has 2 operands, and what are they?
Y and 2.
Yeah, exactly. Y and 2 are the operands. So occasionally I'll say the word operand. It's a fancy word that you never use in speaking normal English, but it's a common programming term. So math operators: times, divide, modulus, floor division, addition, subtraction. Logical operators: equal equal, not equal, less than, greater than, and also these variants: less than or equal to, greater than or equal to, and then the words not, and or. Those are all logical operators. Most languages use these as symbols rather than words. You will see the word not as an exclamation mark. You'll see 2 ampersands to mean the word and. And you will see 2 vertical bars, shift of the backslash above the enter key to equal or. However, not in Python. You'll see me make that mistake every once in a while. If I type this, if x is equal to 3 and y is equal to 2, I'm going to have to go back and fix that. I'll change that to like that. That's about enough. I want to go back and look at our assignment, and we're going to make our next assignment. Our assignment was to do some pseudocode conversions. The next one is just to actually code them. Let's go back and look at the conversion assignment. Make sure everybody got it. All right, the first one was to do kilograms to pounds. Write pseudocode for a program that converts kilograms to pounds, pounds to kilograms, based on this knowledge. 1 pound is that many kilograms. So I give you 2 equations. The requirements. The pseudocode should look much like the pseudocode we've done in class, which I think I tacked one down here at the bottom. Maybe some people didn't actually see that in the other class, and that was resulting in their questions. If we look at it, this pseudocode here, it sure would have been nice if I'd said what it did. To convert feet to inches or meters and back again. That's what I should have put in the pseudocode to explain it. Otherwise, it's just a block of words. So anyways, this pseudocode has us enter feet, and then it does 1 or more calculations. This could have been done in 1 calculation, a longer one, and then does the output. Then it goes the other way. We input the meters, it does 1 or more calculations, and then it does the output. That's obviously very similar to this one, the kilograms to pounds. Now here's what I want the program to look like, or the output to look like. Do not do this. Do not go, okay, I'm going to write a script. Cool deal. I'm going to hit File, New. Oh, yeah. Looks like I'm done. Are you done? No way. Why? Why could I not just copy and paste that stuff and say that that's my program? Because it was in the assignment, right? I'm not trying to be facetious, because people actually do that. This is sample output. It's what I want the program to look like.
You know, if I drew a picture of Pac-Man and I said, I want you to write a picture of Pac-Man,
excuse me, I want you to write a program that'll draw Pac-Man, you wouldn't paste a picture of Pac-Man, you know, into the scripting, even if it let you, and hope that that drew it. You could use this as a basis for your pseudocode if you commented it out and made it part of the documentation. All right, so I'm going to do that. I don't want you to necessarily do that, but I could do that. Sample output of the program. Not a bad idea to have that. It lets the person who comes and looks at your code know exactly what you wanted it to do. So the first line, what is the mass in kilograms? Input kilograms. Good enough. You don't need to write kilograms is equal to int parentheses input parentheses. You know, we're doing pseudocode. It's not a programming language. Then they type something in. Okay, great. The mass in kilograms in pounds is that. Okay, but in order to do that, what do we need to know? We're not going to do this, print 19.8416. What are we going to do? We're going to do the calculation. Pounds is equal to kilograms times, I forget the exact number, I give it to you up there. Then you can print, then you can output the pounds. And I really don't care whether you use the word output or print, but I've used output everywhere already, so I'm sticking with it. There we go. Now we've done these three parts. This didn't specifically say that there was a conversion involved because it's just sample output. We don't tell the user what we're doing. We don't display these equations, but we have to do them anyways. Okay, now we want to do the next part. What should the next line of my pseudocode be? Yeah, we're going to input pounds. That makes sense to everybody? No playing Candy Crush. Okay, what's next? What do I have to do next? Before we can output it.
Calculate.
We got to calculate the kilograms. Yeah. Kilograms is equal to pounds divided by 2.2. And again, that's not the right one, but it's close. And then we can output the kilograms. Now, problems I saw in people doing this is just doing things like this or that. And if you don't see what's wrong with that, it's hard to explain to somebody what's wrong with that. Well, what's wrong with this right here? Why in the world would we output kilograms when we just calculated pounds? We're just going to be printing out the same number that they typed in. That's not good. What's wrong with this section of code? Or, excuse me, pseudocode?
It redefines the pounds,
Yeah,
and it doesn't output anything else given.
right. All of a sudden, kg is being printed, but we didn't do anything with it. So it's actually going to print out the kg from up there, which is not what we're asking for. And here we're changing the value of pounds. Magically, pounds are dividing 2.2. Now, if I was on a diet, maybe I want my pounds to divide by 2.2. But I don't want that in the middle of a calculation. So you just have to track the variables. Okay, input kg, that means that kg is going to be here, not here. Input pounds, that means pounds is going to be here, not here. Now that I'm ready to write it out, do I want to display kilograms? Probably not. I want to display pounds. Now you could come up with a fancy statement, like output kilogram kilos is equal to plus pounds, you know, expressed. I haven't done anything like that in pseudocode. But if you printed that in Java or something like that, if you substitute the word system.out.print, this would actually display the message 22 kilos or 10 kilos is equal to 22 pounds. It doesn't work that way in Python. But, you know, this is getting more complicated. It's doing one of those compound things. We're displaying more information. we don't really need to worry about the details of that when we're writing pseudocode. So I'm just going to make that input, output pounds. I'm going to make this, correct that to kilogram, and then there we go. We have done part A. Part B is extremely similar. There's just one caveat I need to warn y'all about. You know, this one I don't even give you a sample input output because it's so similar to this one. We're going to ask for the temperature in C, we're going to calculate F. We're going to ask for the temperature in F, we're going to calculate C. Why give you sample input twice? We already know. But here's this fancy equation. We need to know something about how to solve that. I don't know if we've talked about PEMDAS yet, have we? Was that a yes or no? Okay. If we type this in, and you didn't know this because we haven't talked about operator precedence. Maybe some of y'all know this in class, from math classes or something, but is that the same thing as this?
No.
And the answer is it's not. Why? Because according to math rules, that gets done first. So that's actually like doing this. Does that look like that equation at all? No, it does not. To fix it, we would put this at the top. That's why I put the parentheses up there, to make it real obvious what was going on. Here, the parentheses are not strictly necessary, but I put them in there for clarity. And so the little rule of thumb is that multiplication and division always happen before addition and subtraction, as long as there aren't parentheses involved. But if there are parentheses involved, that forces them to be done first. There's parentheses involved here, so that would get done first before that. Otherwise, the division gets done first. So if I'd written it like this, C minus 32 divided by 1.8, that's wrong, and this is right. This is part of a larger set of rules. PEMDAS. Please excuse my dear Aunt Sally. Do you have to remember please excuse my dear Aunt Sally? No, but it might help you remember the letters. What this means, P is parentheses. E stands for exponent. MD stands for multiplication and division. Also, modulus and floor division all fall under that same category. Multiply and divide. Then you have addition and subtraction. This is like a hierarchy. This is the most important. Anything that happens in parentheses gets done first. Once the parentheses are sorted out, then exponents get done before anything else. Once the exponents are sorted out, then multiplication and division are handled. Just left or right. It's not that it looks for all multiplications first and then all divisions first. It just goes left or right. Oh, I found a star, I'm going to process that. Oh, I found a slash, I'm going to process that. I found another slash, I'm going to process that. I found another star. Same with addition and subtraction. They're the same priority. They're the same precedence. So it just goes left to right looking for either one. So if you have this, A is equal to 3 times 2 plus 4. Which one of these gets done first according to PEMDAS? The multiply. So that gets evaluated. And really that's not a super awesome example because we would have just thought 3 times 2 would happen anyways. So 3 times 2 is 6 plus 4, which becomes 10. But what if it had been written like this? 1 plus 2 times 3. What happens first? Again, multiply. 2 times 3 is 6. Plus 1. 7. So that becomes 1 plus 6. Which becomes 7. A is equal to 1 plus 2 times 3 minus 2. Just do that one in your head. What does that equal? Yeah, it's 3. Parentheses happen before anything else. Then we start working inside the parentheses. Well, there's only subtraction, so we're all good. 3 minus 2 is 1. Then we have to handle the multiplication. 2 times 1 is 2. Then we can do the addition. 1 plus 2 is 3.
It's funny, 'cause even if you read it from left to right, it would be the same.
Yeah. So this becomes 1 plus 2 times 1, which becomes 1 plus 2, which becomes 3, like that. Exponents the same way. I don't know, you have to give me an example of that. I guess I'll do it anyways. A is equal to 3 times 2 to the 4. Now I don't like 2 to the 4. Yeah. There we go. 3 times 4 to the power of 2. If we didn't know precedence, we might think that this meant 3 times 4, that's 12, to the power of 2, which is 144, which is about as far as my little math table goes. But instead, exponents get done first. So this becomes 3 times what?
16.
16, which becomes 3248, like that. All right, gang, that's about enough. I didn't make an in-class assignment, so let's do the roll.